we should have been talking about gyroscopes all along.
Well, the thing the accelerometer picks up that's causing the issue is gravity. And so you come up with an accelerometer that's giving you one bit of data, and you've sort of got two unknowns. You've got one, which way is the gravity vector pointing, and two, which way is this thing accelerating. Now fundamentally we can make some assumptions that when you're starting out at thrust, this thing isn't moving. And then you can say, okay, gravity's down. We measure a little bit of acceleration incrementally. All right, we know we moved this way a little bit, so we can assume that gravity's pointing down this way. Now we go a little bit farther. All right, we know we moved it a little bit farther. Gravity's now this way. But you've got a little bit of tolerance on each of those measurements, and so as you go along, your gravity vector is getting less and less accurate over time, and so your readings are getting less and less accurate. What the gyro does is it just looks at angular rate. So sitting here, you're getting a 0. As soon as you move, you don't have to worry about the gravity vector. All you see is that you've changed an angle, and that gives you a lot more accuracy. Another problem with the accelerometer is that if it's positioned here, and we make a motion, we know the distance between the accelerometer and the pivot point approximately. And so we can tell how far our angle went. If we are doing something where the device is positioned like this and we're thrusting, now the distance is changing, and our angular measurement is becoming much more complicated. We have to know how far we thrust as well as how much force has been applied. Where with the gyro, it doesn't really matter where the gyro is in the device. Tilt is tilt, and it gives us a result.
So it starts out with information that, I mean, the accelerometer starts out with information that we don't end up using except as a starting point to start calculating from.
Yeah, it's something we just need to subtract out fundamentally.
Right.
And it creates inaccuracies over the long run.
Now physically, it's not a problem getting it in there to fit inside the space it needs to fit.
The gyro versus the accelerometer? Gyro's just about exactly the same size.
Okay,
that's good.
And cost-wise, it's a couple dollars more, right?
The gyros were about $1.50 in 1,000 quantity. I'm sorry, the accelerometers were $1.50, and the gyros are about $4.50.
Okay.
So we've got kind of a $3 adder.
Yes, that's about $3 per unit, right?
Yeah. So the simplification here is going to result in less development time, more overall accuracy, but there will be a cost factor.
Well, it makes sense though. Because the accuracy is working with all these scholastic folks. You know, if they find a hole in accuracy, even though it might not statistically mean anything, they're going to jump on it.
Absolutely.
Right?
Academians are famous for that sort of thing.
So
So
I
are
think,
doctors.
yeah. So I think that makes great sense. I'm glad you caught that. How did you catch that, by the way?
Well, we sat down at lunch and we tried to figure out what the algorithm was going to be for the accelerometer. You know, as you're thinking about it, it just seems obvious. Yeah, we'll just calculate gravity and we'll subtract it out and we'll get the angle. But the reality of it is it's much more painful.
we were sitting on lunch, sitting here with our arms going like this, like,
They were drawing pictures of the restaurant.
Sign language.
That's interesting. I'm glad you caught it.